Okay, so I promised you three lemmas. So this is 1/3 of that promise. Let's first kind of go through the setup. Then this is going to be the punchline, right? The lemma, and then we'll go run through a little bit of a proof. So what's the setup? I want you to think about your favorite Markov chain, and so mine is the Ehrenfest and you can pick whatever the Markov chain you like the best so far from class, or maybe some example from an industry that you want to work in, or maybe from 160A, whatever helps you the most, right? So picture that Markov chain, and we'll call it X. And so the first thing to kind of recognize is, unless otherwise specified, these chains are always homogeneous, right? Time homogeneous, and there's going to be this family of one-step transition probabilities, right? So the PXYs, right? And so these determine how the chain is moving from one state to the next. And anytime you think of a Markov chain X, there are always going to be these numbers, right, associated with the state space S on which the chain lives. And conversely, right, when you're given these numbers, right, that there's this alongside, right, there's this Markov chain that kind of comes to life, and it starts moving on the state space S. So that's the setup we want to be thinking of, and then there are going to be a couple of qualifiers. First of all, there is going to be a stationary distribution, right, and that cannot exist on its own, right? A stationary distribution is a property or a quality of a Markov chain, and so pi is always related to the one-step transition probabilities, and it's a distribution first and foremost, right? So every pi x is greater than or equal to 0. Pi x sums to 1 when summed over x, and of course either a local balance or a global balance condition has to be satisfied, right? So we know that local balance implies global balance, but not conversely. And so I think maybe the important point is to say that when you demand that a stationary distribution exists, we're going to have to outrule some of the chains, right? So not all chains have a stationary distribution, right? And hopefully you can very quickly come up with an example of one. So the statement here, right, is constraining kind of our setup, our experiment, to only certain Markov chains. There's still a lot of them, but not all Markov chains are kind of allowed to be in this experiment. And then this second part is this additional qualifier that at each x, pi of x is strictly greater than 0, right? So what is it saying? It means that every state in our state space S has this eventual probability of being visited, right? After a long time, there's always a positive probability that our chain is in every single one of the states, right? Every single one of the states has a positive probability that the chain is in it after a long time. And so this may seem to be a little bit constraining. You can think about to what extent that's true. In some ways, you could think about what happens when this condition is violated, when pi x is equal to 0. What does that mean? Well, it kind of means that for the type of analysis that we're thinking of, right, a long run analysis, what happens after a long time, pi x equals 0 means the state x is irrelevant, right? And so it never gets visited, and so we might as well kind of throw it out. And so there's a little bit of a catch to what I'm saying, right? Because there are, we'll see, and I think you've probably seen from 168 that there are kind of transient chains where every single pi x is 0, right? The chain leaves all the states. But certainly there are plenty of examples where this is going to be true, and maybe if some states don't satisfy this, we can kind of modify the chain or throw them out, throw those states out entirely. So I don't want to beat a dead horse to death here. I think the setup is mostly clear. So let's get to the lemma. So the lemma is saying, imagine, first of all, it's making a definition, right? So this triangle star triangle with an equality means that the left-hand side is sort of something that has not been in existence so far, right? There's no such thing as pi prime, and we're defining it, right? So this is a definition. Let pi prime p prime xy equal to this right hand side here, right? So that's all that notation means, right? The reason for its use, for those of you who are kind of mathematically inclined, is that an equality means you kind of two things are equal, but the difference here is that this was never in existence, right? We're just defining it, right? Starting from this moment, we're defining what p prime xy is, right? So this is a definition, right? And it's certainly okay to do this, right? Notice that you can right away see why this constraint was enforced. I'm going to divide by something. I don't want to be dividing by 0. And so, clearly this is just, some arithmetic on a few numbers, right? And you'll get a number here, okay? And so I've made this definition, and let's see what the punchline says. The punchline says the collection p prime xy over all pairs xy in the very same state space S, right? The very same one on which the chain X that you've hopefully pictured by now lives on, is a well-defined, right? Also, right, a well-defined family of one-step transition probabilities. So, think about what that means, right? Just to digest this a bit. Clearly, we're defining something different, right? These transitions p prime xy are not equal to the pxy's, right? There's no reason for that to be true, right? This definition looks, kind of complicated. There's no obvious way to say that these two, the p prime xy equals the pxy. So we're clearly defined something new here, and the lemma is claiming that these p prime xy's are one-step transition probabilities in themselves. And so what is this telling us? It's telling us that there's some other Markov chain, right? That's, all of a sudden kind of just, springing to life, right? And it's running on the state space X, just as X is, right? So X is one of, the Markov chain with stationary distribution pi, and these, pxy's are its one-step transition probabilities, which it uses to move on the state space X. And then all of a sudden there's this seemingly very different collection of p prime xy's that's also saying, hey, look, there's another Markov chain, right? And we'll call it, let's say, X prime. And it's also moving around on the state space S. But it's moving potentially with different rules. At least so far, there's no kind of clear way to see if these are equal, if the pxy's are equal to the p prime xy's. So it looks like if this lemma is true, there are going to be two different Markov chains, Markov chain X and a Markov chain X prime, and they're both going to be moving on the state space S. So, there's maybe a lot to digest, and maybe not so much, right? It's in some sense it's simple, but kind of maybe a surprising definition a little bit. But let's run through the proof, and then we'll deal with the consequences. So first, let's see if lemma 1 is true. So first of all, what is it claiming again, mathematically at least? It's saying that these p prime xy's are well-defined one-step transition probabilities. So what does that mean? It means, first of all, that the p prime xy's have to be between 0 and 1. And most importantly, the word transition probabilities, right? This is the most important part. Not only are they probabilities, meaning between 0 and 1, no negative numbers allowed, and no numbers above 1 allowed. But more importantly, it's a transition, right? Which is what I'm going to be trying to argue in this step 2, right? So this step 1 is just kind of a sanity check. I don't want to have any negative probabilities around. That's not a probability. And so hopefully you believe me that this is true. Every p prime xy is greater than 0. Why is that? Well, every single number here, right? There's a division and a multiplication with numbers that are all non-negative, and this divisor here is never 0, and so clearly you'll get a non-negative number here, right? So this step, hopefully I don't have to convince you, is right, kind of a gimme, right? That's an easy one. You may worry whether that's any of those can exceed 1. That's a valid concern, but what I'm gonna say is that proving this is a consequence of also showing this, right? So if we show steps 1 and 2, and we've already seen this before, if we show those two, this one, right, which is step 3, I put a star there because it's optional, meaning that 1 and 2 will imply that every p prime xy is between 0 and 1, right? In other words, when you sum up, right, a bunch of non-negative numbers and they sum to 1, no individual p prime xy can exceed 1, and hence this 3, this is a free, right, this is a kind of a consequence of these two, right? But it's useful to state it, right, because otherwise they're not really probabilities, right? But the point is that we get the third one for free. And let's come back to the word transition, right, and what it means. The transition part is important. Not only are they probabilities, they're also transitions, meaning that starting from every state x, right, this must be true for all x, right, you must go somewhere, right? So summing over the y leads 1, right? This is a statement that every starting state x leads to some state y that the chain is going to be in one step, right? This sum has to be, right, in other words, we move somewhere with probability 1, right? We have to go somewhere from every state x. So, this is going to be just a little bit of algebra. Let me write it in, and hopefully you kind of see how this works. So I'm going to keep the same sum, and just, unless you see something clever, usually you just write down exactly what you're given, and, right, hopefully I got this right. What we're given is this. So I just plugged in the definition for p prime. And now, kind of to simplify things, usually you have a sum, and, you want to take things out of it that don't depend on the summand, right? So what doesn't depend on the y? By the way, this y I should have really written, right, this is overall states S, right, and here again, right, overall states S. So once I take out what doesn't depend on the y, which is this, I will get the following thing. Okay, so I get this. So, hopefully you see kind of how to wrap up the proof. This part right here is nothing other than one of the sides to verifying global balance, right? Global balance is a statement that maybe starting, so the claim is going to be that this is going to be equal to pi x, right? It has to be, otherwise there's no way I'm going to get a 1 at the end of all this, right? And so, hopefully you see that these two are equal by the definition of a stationary distribution, meaning by the global balance equation. This is true, right? The long run probability that we're in state x is the probability that we're in some state y, and we went from y to x in one step, right? And this is summed over all possible y's that we could have been in, including x itself, right? So this is just a statement of global balance, right, that came out after taking out the 1 over pi x. And this is, right, this is an equality, right? This ugly sum is just equal to pi x, and therefore you get pi x over pi x, and that means that this is 1, and so we get a check mark, right? And then finally the kind of step 3, right, falls out for free, meaning when you sum up a bunch of non-negative numbers and the sum is 1, no each individual one can exceed 1, and so you actually have probabilities, right? So step 3, right, is guaranteeing that those are probabilities, and step 2 is responsible for the word transition. So that right, that wraps up the proof, right? And hopefully you've seen sort of what the statement means, right? Just to sum up, we had a Markov chain X, and all of a sudden Lemma 1 is saying, look, there's some other chain X prime. It looks very different, right? These numbers are seemingly very different than the pxy's, and they're both moving on our state space S. So let's see where we can take this in the next clip.